In this video, we'll discuss moment of inertia. Our starting point will be to consider an object, which is just a point mass, moving in a circle around an axis a distance r away from it, and in that case, we can define its moment of inertia to be mr squared. Now, from that starting point, let's consider a conceptual question. Imagine that we have a rod of mass m and length l. We will neglect its thickness. And with this rod, I can define any number of moments of inertia or axes of rotation. We can consider an axis around the center, which we'll call axis A, and it will have associated moment of inertia IA. We're going to consider an axis around the edge, which will have moment of inertia IB. And lastly, we're going to consider an axis through the center. And I encourage you to pause the video and take a moment and consider the ordering of these moments of inertia, and then return once you have your initial guess. So the actual ranking will be that IB is greater than IA, which is greater than IC. And why is that? If we look at axis B, we can see that the average distance, if we imagine breaking up the rod into an infinite number of point particles, the average distance of those particles will be L over 2. So average distance. Here we have L over 2. For axis A, the average distance will be more like L over 4. And for axis C, if we treat the rod as infinitely thin, it would be 0. If we give it some thickness, we could then say a thickness h. The average distance would be something like h over 4. And so that is where we get our qualitative ranking. Now, this is where often a misconception creeps in. And often I have students say, well, let's define the moment of inertia. For B, we can just say it is 1/2 mL over 2 squared. And that would actually be quite wrong. What this does give us is what we would call a lower bound for the moment of inertia. So I can say that IB, the average distance of a particle, is L over 2. However, the particles which are farther away have a larger square value. And therefore, our moment of inertia is going to be strictly greater than mL over 2 squared, right? Because particles which are in the second half of the rod with distances greater than L over 2 are disproportionately contributing to our moment of inertia. So let's go ahead and look at how we're actually going to fully compute moment of inertia. And so we're going to again consider a mass m rod with length L, again neglecting its thickness, and we're going to try to find the moment of inertia about an axis through the center of the rod. Our starting point is that we know I for a point mass is mr squared. And so we're going to go ahead and break up the rod into point masses. Of course, there are an infinite number of such point masses. For the one I've drawn, we can indicate the distance from the axis of rotation, r. And then I'm going to argue that for that point mass, di is r squared dm. And so if I can somehow integrate over r squared dm, we should be able to get our total moment of inertia. Now, as always, when integrating in AP Physics C, my first question is, does r vary with dm? Yes, it does. We can see a dm located right there has an r equal to 0. One out here has an r equal to L over 2. But it's sort of unclear how I can write r as a function of m. And so what do? We need a new integration technique. Our starting point will be to say, I want to write r as a function of m, but m isn't a nicely countable variable. I somehow want to rewrite my variable of integration into something which is spatial. And with that motivation, we're going to introduce the following concept. We're going to define the density of our rod to be the mass it contains per unit length, dm by dl. What I can now say is this is my definition of lambda, but in this particular case, I happen to know the total mass and the total length. They were given to me. And so for that reason, we can say dm by dl is equal to total mass over total length. With that, I can rewrite my integral. I can say dm is equal to mass over length times dl, simply rewriting our density relationship. Having done this, it's not yet exactly clear what I've accomplished, right? But remember, DL is a general coordinate representing the length of our rod. In this case, our rod is located along the x-axis. And so I'm going to say that DL is equal to dx. And so my integral is now pull out constants, m over L are constant, integral r squared dx. Next step, I'm going to introduce a coordinate system. We'll say x equals 0 is the center of the rod. And with that established, what I can say is, if I know the x coordinate of my dm, r squared is exactly equal to x squared. And so I'm left with m over L integral x squared dx. And lastly, I can define my bounds of integration to be negative L over 2 to L over 2, since my rod has a total length L. And from there, we get m over L x cubed over 3, evaluated from negative L over 2 to L over 2, which simply becomes 1/3 m over L times L over h, L cubed over h, plus L cubed over h, or 1/12 mL squared.